Hi everyone. Welcome to the lecture for Chapter 11, all about water. I apologize for the delay in posting this lecture. I posted the rest of the module, but I was having issues with the microphone on my computer, which apparently now has been solved by the wonderful computer people at my university. But for a while it wasn't working and I couldn't get any sound on the videos. But today we're going to talk about water. We're going to talk about everything from water usage to water pollution to water conservation. So your book gives the example of Lake Chad in Africa, which this area was much wetter about 5,000 years ago. And the lake has receded ever since. And a lot of people rely on this lake. So it's receded for a few reasons. It's receded over 90% since 1973. One, due to climate change and global warming. The second is due to deforestation in the region. And the third is due to overuse of that water system. And the other question is, as a water resource, who owns the waters of Lake Chad? Because the human population there surrounding the lake has increased threefold, placing increased demands on its fisheries and water for irrigation. So it's an incredibly important water resource that is shrinking. So you can tell from these images here, just how dramatic the shrinking of Lake Chad is to the local residents, which spans several countries. So we're going to look at water. We want to think about it as kind of a resource that very often goes across borders. And that very often we are using at unsustainable rates, or that is getting increasingly unpredictable due to climate change. So the first thing that I want to talk about is the global water budget, or what does water look like on our planet? So over 70% of the Earth's surface is covered with water. A lot of that is not particularly useful for us, right? Because it's seawater and ocean water. Um, Equal amount of water evaporates as precipitates. And so what I mean by that is, what goes up must come down. Water evaporates into the atmosphere, right? Off of surface bodies of water, but also through evapotranspiration is when it evaporates through through plants. And then it comes down, it flows over land into rivers and streams, but then it also percolates into groundwater. And groundwater is connected to rivers and streams. They're not totally separate systems, which we'll talk about a little bit later when we get into groundwater. Um, Also very important is atmospheric water. If you were in my physical geography class, I spend quite a bit of time talking about atmospheric water. It is a very, very, very small portion, 0.001% of Earth's water. But again, atmospheric water, right? What goes up must come down eventually. And so that's how we get a lot of our precipitation and weather, right? So a huge amount of annual water flux in and out of the atmosphere. So here you have almost 500,000 cubic kilometers of water that is going in and out of the atmosphere. So while the atmosphere at any given moment only contains about 12,600 cubic kilometers, right? It is really recycling a lot of this water. And 23% of that precipitation that comes down falls over land. If it falls over the ocean, we can't capture it. It's no good to us. And out of that terrestrial fresh water supply, 2/3 of it evaporates right back up, and the remainder flows into streams or rivers or percolates into that groundwater. And so Your chapter talks about the hydrologic cycle and how water is circulated throughout the planet. So all of the water that exists on the planet is all of the water that has always existed and all of the water that will exist. So we're not creating new water. It's just moving throughout the system, being cleaned and being recycled. So the amount of water is constant, but where it is at any given moment, changes, right? So it's not that we lose water or gain water, globally speaking, but we, you know, if we go through a drought, that water that might have been there is now someplace else. So again, water evaporates off of surface water, off of the water in the oceans, off of plants. It goes up into the atmosphere, it condenses, it falls as precipitation, which is not just rain, but also ice and snow, rains down, either falls back into the ocean or falls as surface water, where then it some of it evaporates immediately back up, or it percolates down into groundwater and surface water. The other important thing to know is the idea of watersheds. This is a map of all the watersheds in San Diego County. Watersheds are the area of land that drains to form a river or a lake. So basically, when you're looking at this map, if we look at the Tijuana River watershed, all the precipitation that falls in this entire area that does not evaporate back up will wind up in the Tijuana River at some point or connected to its groundwater. These are also called drainage basins. They are separated by geologic features, mountains and plateaus. So basically you have a peak or a ridge here, so everything on this side of the ridge goes into San Dieguito, every side on this side of the ridge goes into Peñasquitos. We have open watersheds that eventually drain into the sea, such as all of these watersheds right here, or we have closed watersheds that do not drain into the sea. Those are called endorheic basins. And for example, closed watersheds are things like where the Great Salt Lake is, because closed watersheds, because those minerals are not continuously flowing into the ocean, those watersheds get saltier and saltier over time. That is why you have salty oceans, is because that surface water and groundwater picks up minerals and salts and eventually deposits them into the ocean. When you're in an endorheic basin, it's not getting out into the ocean, it's depositing into a lake. And so that's how you get these salty inland bodies of water. Right, and so here is an illustration of a watershed. Basically, here is the boundary between the watershed, and all the precipitation that falls on this side is going this way, all that falls on this side is going this way. Watersheds can happen at multiple scales. So all of this area here eventually drains into the Mississippi River. The watershed for the Mississippi River as a whole is enormous, but you could also talk about the watershed for the Missouri River or the Upper Missouri River or the Ohio River. You can take these down again to smaller and smaller scales, or talk about gigantic watersheds. And this is also, too, a separation for the continental divide right here, which I'm not going to talk about in this class, but basically all of the precipitation that falls on one side of the country winds up in the Atlantic Ocean, the other side winds up in the Pacific, and then we have a big endorheic basin. There's that Great Salt Lake right there. Next, I'm going to talk about, we talked a lot about ecosystem services in past chapters, but I just want to highlight some of the important ecosystem services that water provides for us, ones that are essential to life as we know it. We need them for supporting services. We need the hydrologic cycle for things like photosynthesis, excuse me, nutrient movement, and food webs, right? All of these things rely on that water system moving around. Also regulatory surfaces like temperature regulation and pH buffering. So we need to make sure that we have water that's at a pH that enables and promotes life. Excuse me. And then provisioning services, which are probably the ones that you most associate with the water cycle, right? We need water for drinking water and we need it for agriculture to grow our food, right? Most of the food in this country is grown through irrigation systems, not just through precipitation that is falling down. If you're in a country like India, up to 60% of the agriculture there still reliant on the water cycle, but it's done through the natural monsoon season. So they are particularly susceptible to shifts in climate change. Um, human water use, we use over half of the water flowing in Earth systems. And so this is not water that is trapped, that is unavailable to us, like in the ice caps. But water that is available to us, we use over half of it. And we use it for two different types of uses, non-consumptive uses and consumptive uses. Non-consumptive uses are water uses that returns that water to the stream or aquifer. So you can think about hydroelectric power, right? We are going to hold that water behind a dam. We're going to release it. It's going to turn a turbine. We're going to get electricity, but then that water is eventually going to go right back into that place. Or, a wastewater in a septic system, you're taking some of that water out, but then it is eventually going back into the system. Or then you have consumptive uses where the water is not immediately returned, such as irrigation, right? We're pulling that water out of the Colorado River and we're putting it down canals and we're taking it to farms, so it's not immediately going back into that river, or a wide variety of industrial uses. So when I want to talk about the amount of water on the planet, the amount of fresh water that's available to us is actually very, very, very small. So where is the Earth's fresh water? The Earth's surface water accounts for about 70% of the water on Earth, but 97.5% of it is salty or or frozen and or in soil. So only 1% of that 70% of surface water is fresh water. And if you look at total global water, about 2.5% of total global water is fresh water. But fresh water is not evenly distributed, right? So here is, this explains it a different way than this. But so if we have 96.5% is in the oceans, 2.5% is fresh water. Almost 70% of that fresh water is in glaciers and ice caps. Another 30% is underground, which may or may not be accessible to us. Only 1.3% is surface water that is fresh. And then after, or other fresh water, and after you take that, you still have atmospheric water, ice and snow, right? Very, very, very small percentages of water that are available to us. And it's not distributed evenly globally, which we know. We have drier places and we have wetter places. So we have something called baseline water stress, which is the total annual water withdrawals as a percentage of annual flow in that region. So some places have a much higher baseline water stress than other places. So if the next slide will be a map, we can see here, right, we have extremely high baseline water stress in Southern California. We've recently gone through droughts. We grow a lot of food here. We pull a lot of water out of a system. We import a lot of water. We compared to the available flow of water in our system, we pull a heck of a lot out. As opposed to a place like the Amazon in Brazil, lots of water compared to what's being pulled out. So this isn't necessarily the amount of water that is available, but it is the amount compared to what is being pulled out of the system. Next, I'm going to talk about groundwater. Groundwater is water that resides in rocks or soil beneath the ground. It is a small percentage of Earth's total water. It's 0.3%. By the way, all of these percentages, I'm not going to ask you on the quiz what is the percentage of Earth's groundwater versus total water. You don't have to remember these numbers. It's just to give you an idea of exactly how small that is. Most of it is in aquifers, and aquifers are layers of sediment and rock that are saturated with water And they have a wide variation of volume of water stored. We have some very, very large aquifers, such as the Ogallala Aquifer in the center of the United States, that is used for agriculture, but very often groundwater takes a very long time to recharge. So we're often using groundwater at a much faster rate than we can replenish it. And so there's a couple things that I want you to know about groundwater systems and how they work. So basically here is a confined aquifer. This is a layer of saturated ground. And so you know, somebody has a well here that's gone down into this aquifer. Here's an unconfined aquifer, right? It's connected to the above ground system. Here's a shorter well that's going into that system. But what I want you to know is the idea of a water table. So while this is not true in Southern California, because we have a pretty dry climate, when I grew up in Connecticut, you could dig a hole, as little kids tend to do sometimes. You could dig a hole and you could get down, you know, a little bit of a ways, and it would start to get some water in it because the groundwater was fairly close to the surface. And so if you are near a stream or a lake, this water table, this top of this saturated area, is right in line with the stream and is connected to streams and lakes and rivers. So when you see the height of a stream here, it is connected to this underground water system. And so if you get pollution into the stream, you have the possibility of contaminating this groundwater. If you you know, get some contamination over here, it's possible to get it in the stream and affect wildlife that are in that stream and anybody else who is using that. I'm also going to talk about areas that have no recharge. So you have areas where you have groundwater, but it's now currently not being replenished at all. So rain fell over 5,000 years ago that created this Nubian sandstone aquifer beneath the Sahara Desert. This aquifer is providing a lot of water to the area, but it's going to be depleted and it's not going to recharge, right? So unlike the Ogallala Aquifer in the United States, which is being used at a faster rate than it can be replenished by nature, this one's not going to be replenished at all because this is very, very old water that they are pulling out. So once this aquifer is gone, it is gone. Also with groundwater, I want to talk about how we use groundwater. We extract quite a bit of groundwater. Again, you don't have to know these numbers. From groundwater systems, a huge portion of that goes to agriculture, about 68%, 21% to industrial use, 11% to domestic use. And again, some areas, their extraction, particularly in arid areas, exceeds the recharge, which means those are going to deplete, and then that's going to be it. It is the primary source of drinking water for many people, whether that is your town or municipality is pulling from groundwater, or there are lots of people who live in rural areas that you know, have pumps that pull out water out of groundwater, and it is a very scary thing if you turn on the faucet and no water comes out, because you may have to dig a whole new well that's going to go a lot deeper in order to get that water. And then we also have problems with pollution of groundwater, things like faulty septic systems or chemical storage tank leaks. You can also get leaks from you know, landfills and waste systems. And people are continually concerned about potential contamination due to hydraulic fracturing as well. That hydraulic fracturing to pull this natural gas out is pumping in all of these things and contaminating groundwater systems. The next thing that we're going to talk about is water quality and water pollution. So ideas of water pollution, those standards differ with use, which means that what you would consider polluted recreation versus polluted drinking supply water is very different. Often when you have reservoirs that are for drinking water, there's no human use allowed on those reservoirs. But you know, what is good for recreating might not necessarily be good for drinking. But water pollution is defined by three prime characteristics. The first one is a physical characteristic, and that is turbidity, which you're seeing a picture here of that. Turbidity is the amount of sediment that is in the water. And so whether the water is cloudy or clear, so that's a physical pollution. Then there's chemical pollution, which is industrial discharge. Pharmaceuticals, we increasingly have lots of antibiotics in our water due to it running through people and animals and then winding up back in the water system. Also, personal care products can be a big problem. In addition, if you ever buy products that have microbeads in them, whether it's a lot of places have tried to ban microbeads, whether it's face wash that's like a gentle exfoliant with microbeads, or even toothpaste, because you're not technically supposed to swallow toothpaste. Those are actually tiny pieces of plastic that then wind up in waterways. They're really not great for the system. And then biological pollution, so things like bacteria and pathogens. So if you are, have are a bunch of cattle next to a waterway, you could potentially get E. coli into a waterway. When we think about clean water, or what are the standards for clean water, we think of it in total maximum daily loads, which represents the maximum amount of a pollutant that a body of water can support without reducing water quality below acceptable levels, right? So you can have a certain amount of certain things in water, but once you get to that point, then it's considered polluted and it's no longer usable. The EPA, or the Environmental Protection Agency, requires states to report impaired waters that surpass that TMDL. And you're going to watch a short video, if you haven't already, about the Flint water crisis after you watch this lecture. And the top impairments that get reported to the EPA are pathogens. So again, biological impairments, heavy metals like the lead that was reported in Flint, or nutrients. And so we're going to talk about nutrient pollution and what that looks like, which results in something called eutrophication, which I'll get to talk a little bit more about in a minute. And I'm going to talk about a few ecosystems now and kind of the types of water pollution that they faced. I'm going to talk about lakes and streams and estuaries, and then ocean systems. So first, we're going to look at the effects of water pollution on streams. When stream water can get polluted, it can devastate local biodiversity. So today, over half of the 308 species of freshwater mussels native to streams in the United States are either endangered or have gone extinct. These are filter feeders. They are especially vulnerable. And a lot of this happens due to heavy metal from mining, especially in places like Appalachia, where there was a lot of coal mining, mountaintop removal, and then you also have pH being altered due to that mining as well, which has really kind of devastated a lot of local waterways and a lot of local biology. And then we're going to talk about lakes, right? So lakes often, this is where I'm going to talk about that nutrient pollution, but you also have nutrients that accumulate from runoff. And this can happen due to stormwater or factories or farms, right? So if you think about it in terms of a farm, you have a farm that is using a bunch of fertilizer. That fertilizer, those nutrients are going to, whatever is excess after it rains and it's irrigated, is going to run off into that local waterway. And then so you get this eutrophication, which is the enrichment of bodies of water with excess nutrients. And so you might think, well, what's wrong with some excess nutrients in water? Generally thinking of nutrients as a good thing. But what happens is you get algal blooms. So like what you see here, you have this huge area that you get these, they're often seasonal, where you get this huge amount of algae. And then you basically get large amounts of organic material decomposition that then uses up a lot of oxygen. And so basically it chokes a lot of things out. And then you wind up with reductions in biodiversity in these eutrophic lakes. And so actually, I think it was northern Lake Erie, part of Lake Erie, that basically the residents are trying to pass a bill of rights for the lake due to this yearly eutrophication process that's happening. So basically the residents are trying to get a way to protect the lake from this continually occurring every year. And then we're going to talk about estuaries. So estuaries are basically the base of watersheds, and it's often where many pollutants enter. And again, we can have excessive nitrogen and phosphorus eutrophication, so that same process that we saw in lakes. But this can lead to massive dead zones where you have oxygen that is so low that few marine organisms can survive, right? So if you pull all of the oxygen out of an environment and you essentially get an anaerobic environment, not much is going to live there. Estuaries are important because a lot of things reproduce in estuaries. They are extremely important. And then in oceans, again, the same ideas. You can get dead zones. The UN estimates that there's over 200 dead zones in the oceans. All of them are associated with a mouth of a river where you have pollution coming out of the mouth of that river. And they are a major contributor to the decline of fish species. So we are generally overfishing pretty badly. And it is not helping this cause that fish are already declining due to these dead zones. It also hurts coral reefs, which are on the decline due to climate change. We'll talk about coral reefs a lot more when we get to climate change. And you also get this accumulation of mercury in large fish. So if you have ever been pregnant or know somebody who has been pregnant, if you are you're not supposed to eat a lot of tuna because tuna is a large fish and they accumulate a lot of mercury. So basically you have species at the bottom that are accumulating mercury, but then as you go up that food chain, that mercury concentrates. And it's really not good for your system to have a bunch of mercury in your system. And then also oil, right? So in the Gulf, we had massive oil spills. We can get smaller oil spills and discharge that pretty gravely affect these ecosystems as well. So also looking at oceans, we also have problems with acidification, which is the reduction in pH due to increasing CO2 input, right? So 25% of CO2 in the atmosphere is absorbed by the ocean. The ocean is an important holder of greenhouse gases, and acidification limits the calcification of many organisms. And so what that means is it really slows down coral growth and hurts a lot of other species as well. So you often hear of ocean acidification as a reason for this declining coral, and it's become kind of a very big public policy issue. Another issue with pollution and the oceans is trash. Basically plastic trash, including those microbeads that I talked about, but lots of other plastic trash flows into the ocean. And basically, winds and currents concentrate this trash. We have something called the Great Pacific Garbage Dump, where we have 4 million tons of plastic over 1.2 million square miles. It is a massive plastic gyre that's full of everything from plastic grocery bags to water bottles and bottle caps and a whole bunch of other really nasty stuff. So it is fairly large, and a lot of it, this picture, they kind of cover up most of it, but you have atolls out in the Pacific that look like this, where massive amounts of plastic just wash up on shore. And while the big plastic is really a problem, plastic will continuously break down into smaller and smaller and smaller pieces. And what you wind up with is this like plastic soup. And those tiny pieces are eaten by wildlife because wildlife think those are, great little things to eat. And they eat them, and then they wind up dying from that. So you have lots of birds where after they die, researchers find their bodies on these atolls and their stomachs are just completely full of plastic. And so it's really hard to clean up. You can imagine if you have some water that has a bunch of tiny, tiny pieces of plastic in it, and now you're talking about something over 1.2 million square miles, how are you potentially going to clean anything like that up? Next, we're going to talk about water management and conservation, which is what I'm going to talk about for the rest of this lecture. So kind of what are the issues with water management and conservation? How do we deal with water management and conservation? This is a picture on the right of Oroville, Lake Oroville during our most recent drought, right? You can tell the water was significantly lower. It has since come back up in the past couple of years with all the rain we've had. But 7 million people a day, or 7 million people globally, excuse me, live with water scarcity, right? So they consistently do not have enough water for their needs. More than 3 times that lack access to clean water. So, we kind of take it for granted, maybe not if you live in Flint, Michigan, that you kind of turn on the water faucet and clean water, drinking water comes out. But that is not true everywhere. It is most acutely felt in poorer countries. Kind of ironically, the places that are the poorest usually have the most expensive water. But wealthy nations also face water shortages, which we certainly have in Southern California. And some people estimate that we are going to see a 50% increase in water use by 2050. So we don't seem to be declining in our water use at all. And then there's the question of climate change. How is this going to switch where water is available? So the conservation of water is a key aspect of sustainability. We want to make sure that we have enough water and that we're using it wisely, considering that we are going to be increasing our water use, especially as population goes up. So a couple of things that we do, we regulate the flow of water. Rivers and streams are modified to reduce flooding, whether, the most common way to do that is with dams, but there are other ways that we modify rivers as well, but we do it for not just to protect ourselves from water shortages, but also to keep places from flooding. We also do it to generate hydroelectricity. In the US, we have over 79,000 dams that are higher than 7 meters, some that are quite big, some that are not that big. But they essentially change an ecosystem. They affect animal movement. So, salmon can't get upstream to spawn once you put a dam in there, although some have kind of fish byways that help a little bit. They reduce of water flow downstream. They alter seasonal water flow, or we are controlling what happens downstream. they change sediment movement. So as erosion happens from overland water flow, that sediment normally gets carried down to a floodplain. It replenishes, like if you think about coastal Louisiana, which is losing a lot of land every day because it's not being replenished, all of that backs up behind a dam. And so it's not making it downstream. So it's really kind of affecting what those downstream areas look like. We've also lost a lot of wetlands. Um, Wetlands are extraordinarily important. They are critical in mitigating flooding and storm surge. And so what storm surge is when we think about Hurricane Katrina that came ashore in Louisiana, and Louisiana has lost a lot of their wetlands. Basically, as a hurricane comes ashore, it kind of pushes this kind of wall of water, not like a tsunami, but um, uh, this, a large amount of water kind of pushes the tide up on shore. And wetlands can slow that down and mitigate that quite a bit. They can also slow down a hurricane in general. And as we've lost that, you get the storm surge that comes in. It's the storm surge that caused that massive flooding that was so devastating during Hurricane Katrina. But in the past 200 years, wetlands in the lower 48 states have been reduced from 90 to 40 million hectares. So we've lost quite a bunch of that. Again, a bunch of that along the Gulf Coast. And then nutrient pollution and other types of pollution have really degraded the function of those wetlands as well. We've, had issues with mosquito control and agriculture. So again, we lost incredible amounts of wetlands. We gained some here. People have started building wetland mitigation banks, which I'll talk about again in a second. But basically, if you have to destroy a wetland in one place, you have to, build wetlands someplace else. So many countries have set up policies to stop the loss of wetlands because they're so important. In the US, there is no net loss policy, which means there's no we cannot go below this much wetlands. There's kind of more it's based upon the Clean Water Act, so it's more based upon can the system withstand that? But if a wetland is destroyed or impaired through development, generally speaking, an equal amount must be restored or protective. So it's not that you cannot destroy a wetland anymore due to construction, but you basically have to build wetland or protect it somewhere else. So there's a lot of wetland and restoration projects underway. This is a formerly drained and degraded marsh near Seal Beach, California, that has been restored. And so now it can kind of perform those important ecosystem services that it could not do before. We also want to think about crop irrigation. We lose an incredible amount of water to crop irrigation. 70% of freshwater use irrigates crops, and it's often done really inefficiently. So where you have this only very small percentage of the water being applied gets used by the plants. And so a lot of it just either runs off or just evaporates. We're pulling water out of one system, not effectively using it on our farms. Most farms operate at less than 40% efficiency, but simple changes in practices and new technologies can decrease this use by 15 to 50%, right? So here's a picture of drip irrigation, which drip irrigation makes a lot more sense. It can be expensive to install, especially on large farms, but basically you have this tube that there's a small hole in the tube, and that water is coming out directly on that plant. So as opposed to just spraying an entire field with water with lots evaporating off, we are really applying water directly to a plant in order to sustain that plant. When we think about water reuse, which if you took my sustainability course last semester, we talked a little bit about water reuse and gray water and toilet to tap, and which I'm going to spend a little bit less time on today. But recapturing water and reusing it, it can conserve water and provide lots of benefits, especially because if you, um, if you use municipal wastewater and you reuse it for irrigation, reused water has residual nutrients in it, so it reduces your fertilizer needs and it reduces needs for water to be pulled out of the system in the first place. So often you will see, especially, I think you can see it around campus where there's signs that says like irrigated with reclaimed water. So this is wastewater that has been treated and then applied for irrigation purposes. So I want to talk a little bit about water and you, right? So what does your water use look like? And your writing exercise for this module is based upon your own water footprint. You're going to take a water footprint calculator to calculate your water footprint, and you're going to answer some questions about it. But in the US, 13% of fresh water is used by municipal water systems that are going to your average citizen. Bathrooms and laundry use the highest proportions of water, with toilets, washing machines, and showers being the biggest users, right? So taking long showers or baths, flushing our toilets, all of that other great stuff uses a lot of water. We have gotten fairly good at conserving water in our homes, especially in places like Southern California, where we have a lot of kind of low flow toilets and faucets and high efficiency washing machines that have really reduced that indoor water use quite a bit. So when you think about how much water do you use, and so this is direct water use, right? As in, I am turning on a faucet or using something and directly using water in my house or on my lawn. Average American uses 300 to 378 liters of water per day, which is quite a bit, right? So think about washing your clothes, flushing the toilet, drinking water, showering, all that other stuff. Only 8.7 liters per day are needed for survival, right? Which is not really what we want, just survival. But the World Health Organization says about 20 to 50 liters per day for basic human needs, depending on where you're living. So we are definitely exceeding that in the United States for our basic human needs. So you can track how much water you use per day. You can record your direct use of water over the next 24 hours in your bathroom, the laundry, and the kitchen, and the water you use outside to wash your car and water the lawn. And then you can think about what conservation measures you can live with. So I encourage you, as you do that water calculator, to think about these things. That water calculator, based upon what you're doing, tells you different things that you could do to save water. But what your textbook doesn't really talk about as much, and in fact, I'm not sure if your textbook discusses it at all, and what this calculator talks about a lot is virtual water use. Virtual water is all of the water that goes into goods and services. So we have virtual water that we use every day, whether it's for putting gasoline in our cars. That gasoline took a certain amount of water to produce. The food that we eat is a big one. It is part of our individual water footprint. The clothing that we wear, cotton, is a very large consumer of water when it is produced. So that is also going to talk about your virtual water use, and you're going to answer some questions about your virtual water use as well. So I want you to think about virtual water use, because a lot of times people tend to be very disconnected from that. The last thing we're going to talk about is policy and law that is used mostly in the United States in order to decide who gets to use water and how water is conserved. So in the US, the states set water use rights, but it is dramatically different in the eastern United States than it is in the western United States. So in the eastern United States, we have riparian water rights, which means that landowners adjacent to water have right to reasonable use. They can take out a reasonable amount of water. they can't take it all, but they can take out a reasonable amount just because you are adjacent to it. And in the western states, they have prior appropriation water rights, which means the rights are not connected to the land and may be bought or sold like property. So California has senior water rights over Arizona, over the Colorado, because they claimed it first, which is a little bit weird, right? It's not based upon who has most of that river in their area. San Diego County, way back when, claimed part of the Colorado by writing it on a piece of paper and leaving it in a tin can next to the river. So it's not about owning that. And also, again, you can buy water rights. People can sell you their water rights, which is very different from the East Coast. We also have several laws in the United States that were passed to manage water. So in 1899, you get the Refuse Act, which is the first attempt to manage water quality at a national level. And this basically stated that waste could not be dumped into navigable rivers without a permit from the Army Corps of Engineers. Then you get the Oil Pollution Control Act of 1924, which regulated the dumping of oil from boats, but not from stationary sources, such as like a factory could dump oil, but boats could not do it. And so these kind of diminished water pollution a little bit. But then you get the Water Pollution Act of 1948. And this is kind of the first big national law that's passed to manage water quality. And it provides grants to local governments to clean up water, and also the ability to sue water polluters in court. But the true kind of big law that has teeth is the Clean Water Act of 1972. So you get the Clean Water Act, you get the Clean Air Act right around the same time, and the establishment of the Environmental Protection Agency. And this is due to like this rising public awareness of pollution. And this is a picture of the Cuyahoga River fire. I mean, rivers used to be so polluted that some of them you could literally throw a match in and they would ignite. So, you also get the rise of kind of, TVs being in everybody's home and these things being more publicized. So people seeing things like rivers catching fire and demanding action. And then internationally, you get the 1997 Convention on the non-navigational uses of international water courses, which, basically prevents some discharges on international waters. But generally speaking, protecting water is hard to do on the open ocean, right? There's nobody out there regulating the open ocean that is patrolling it. So it is mostly a domestic issue for most countries. So that is the end of your lecture on water. You're now going to move on to that short video about the Flint water crisis, your writing exercise, and your quiz for this module.